When setting up a generator to power a subpanel, it's critical to ensure the existing electrical system is safe and up to code. A common issue arises when the subpanel feed, the wiring connecting the main panel to the subpanel, is undersized. This can create significant safety hazards, particularly concerning fault current and the potential for fire. Let's break down why this is a problem and how to explain it to someone who might not be familiar with electrical concepts. Imagine the electrical system as a water system. The main panel is like a water tank, supplying water, or in this case power, to the subpanel through a pipe or the service entrance cable. If a fault occurs in the subpanel, such as a short circuit, the current will seek a path back to the main panel. The service entrance cable feeding the subpanel must be appropriately sized to handle the potential fault current from both the main panel and the subpanel. If the service entrance cable is undersized, it cannot safely carry the fault current. A no-fault path is a dedicated grounding conductor that provides a low impedance path for fault current to return to the source, which is the main panel. This path is essential for quickly tripping a circuit breaker or fuse, disconnecting the power, and preventing dangerous voltage from appearing on metal parts of appliances or equipment. Without an adequate fault path, fault current could flow through other paths such as the grounding conductor or even metal conduit, creating a risk of electric shock or fire. Objectionable current refers to current flowing on the grounding conductors of an electrical system. This is generally undesirable because grounding conductors are intended to carry current only during fault conditions. When objectionable current flows continuously, it can indicate a problem with the wiring, such as a ground fault or improper neutral connections. This current can cause the grounding conductors to overheat, potentially leading to a fire. It can also interfere with the operation of sensitive electronic equipment. If a fault does occur, the excessive current can flow through an undersized service entrance cable, causing it to overheat and potentially start a fire. To illustrate this with an analogy, imagine a fire hydrant with a 2-inch pipe connecting it to a house. Then connect another 1-inch pipe from the house to a second hydrant. If there's a fire, the water will flow back through the 1-inch pipe, causing it to burst because it's too small for all the water. The same principle applies to electricity. Now consider a scenario where a 200 amp main breaker panel feeds a 100 amp subpanel using number 2 service entrance cable with 3 conductors. According to the National Electrical Code, number 2 copper conductors with type TW insulation, which is a common type of insulation, are typically rated for only 95 amps at 75 degrees Celsius. While some types of insulation, such as THHN or THWN, allow for higher ampacities, it's crucial to verify the specific insulation type and temperature rating of the conductors being used. If the conductors are only rated for 95 amps, they are undersized for a 100 amp subpanel. This means that the conductors could overheat if the subpanel draws more than 95 amps, potentially leading to a fire. The National Electrical Code section 310.15 outlines the requirements for conductor ampacity, and it's essential to consult the section to determine the correct conductor size for a given application. Table 310.16 provides ampacity ratings for various conductor types and sizes based on their insulation type and temperature rating. This table is a crucial reference for ensuring that conductors are properly sized to handle the expected load. Moreover, the overcurrent protection device, such as the circuit breaker or fuse, must be sized to protect the conductors from overcurrent. According to the National Electrical Code section 240.4, conductors must be protected against overcurrent in accordance with their ampacities. This means that the circuit breaker or fuse protecting the number 2 service entrance cable should not exceed the ampacity of the conductors, which in this case would be 95 amps if using type TW insulation. If the circuit breaker is rated for 100 amps, it's not providing adequate protection for the conductors, and they could overheat if the subpanel draws more than 95 amps. This is a critical safety concern that must be addressed to prevent a fire. Let's discuss some common scenarios and potential solutions. Firstly, if the existing number 2 service entrance cable is indeed undersized, the most straightforward solution is to replace it with a properly sized cable. For a 100 amp subpanel, a number 1 copper conductor with type THHN or THWN insulation would typically be required. These conductors are rated for 110 amps at 75 degrees Celsius, providing adequate capacity for the 100 amp load. Secondly, it is essential to ensure that the grounding conductor is also properly sized. According to the National Electrical Code Section 250.122, the size of the grounding conductor must be based on the size of the overcurrent protection device protecting the circuit. For a 100 amp circuit, a number 8 copper grounding conductor is typically required. Thirdly, if it's not feasible to replace the entire service entrance cable, another option may be to reduce the size of the subpanel's main breaker. If the subpanel's load is typically less than 95 amps, it may be possible to reduce the size of the main breaker to 90 amps or less. This would provide adequate protection for the existing number 2 service entrance cable. However, it's crucial to carefully evaluate the subpanel's load to ensure that it will not exceed the reduced breaker size. Before making any changes to the electrical system, it's essential to consult with a qualified electrician to ensure that all work is performed in accordance with the National Electrical Code and local electrical codes. An electrician can assess the existing wiring, determine the appropriate conductor sizes, and make any necessary modifications to ensure the safety and reliability of the electrical system. Now let's talk about the implications of the generator installation. When adding a generator to power the subpanel during a power outage, it's even more critical to ensure that the wiring is properly sized. The generator will be supplying power to the subpanel, and any fault current will flow back to the generator through the service entrance cable. If the service entrance cable is undersized, it could overheat and potentially start a fire, especially if the generator is capable of supplying more current than the cable is rated for. To properly install a generator with a transfer switch, firstly, ensure the transfer switch is rated for the appropriate amperage and voltage. A 100 amp transfer switch is suitable for a 100 amp subpanel. Secondly, the transfer switch should be installed in accordance with the manufacturer's instructions and the National Electrical Code. This typically involves connecting the generator's output to the transfer switch, and then connecting the transfer switch to the subpanel. Thirdly, a grounding electrode conductor must be connected from the generator to a suitable grounding electrode, such as a ground rod or the building's grounding system. This ensures that the generator is properly grounded, providing a path for fault current to flow back to the generator. The National Electrical Code Section 250.30 provides detailed requirements for grounding generators. Now about the customer signing off on the issue of the undersized subpanel. While it may seem like a way to protect yourself from liability, it's important to understand the limitations of such a document. Firstly, a waiver does not absolve you of your responsibility to install the transfer switch correctly and in accordance with electrical codes. You are still responsible for ensuring that the installation meets all applicable safety standards. Secondly, a waiver may not be enforceable in all jurisdictions. Some courts may find that a waiver is invalid if it violates public policy or if it was obtained through fraud or duress. Thirdly, even if a waiver is enforceable, it may not protect you from all potential claims. For example, if someone is injured or property is damaged as a result of the undersized wiring, you could still be held liable, even if the customer signed a waiver. It is crucial to document the customer's refusal to correct the underlying issue clearly. This documentation should include the date of the inspection, the specific problems identified, the recommendations made to the customer, and the customer's response. The documentation should be signed and dated by both you and the customer. Remember, your primary goal is to ensure the safety of your customer and their property. If they are unwilling to address the safety hazard, it's best to decline the job rather than put anyone at risk. Explain to the customer that you are not comfortable installing the transfer switch until the wiring issue is resolved. Let them know that you are concerned about the safety and that you cannot compromise your professional integrity by installing a system that you know is unsafe. If the customer is still unwilling to correct the wiring issue, you may want to consider terminating the relationship. It's better to lose a customer than to risk someone's safety or your professional reputation. Ultimately, it is very important to make sure the customer understands and address the problems.